digital electronics and computers of all types, and really all digital devices, depend on number systems at their roots to represent all the various types of data, whether it be numerical data, text, video, or any other type of image file or any other data that we could possibly consider. So some key terms and concepts will be the number system itself, place value, the decimal number system, binary number system, octal number system, hexadecimal number system, and then of course base conversion, so we can go between the various number systems. So we're going to investigate number systems and learn how to convert from one system or base to another. And number system uses a set of symbols to refer to a collection of sequential items. The first number system that we're going to consider is the common decimal number system. And as you may or may not know, this is base 10. So we have the available values or symbols that we use for the decimal number system, ranging from 0 through 9. So when we include 0, of course, we have 10 different possible symbols. So humans use this type of system for counting and other mathematical calculations. And central to any number system is going to be place value. So consider, for example, the number 382. And we also represent it in a decimal to distinguish it from the other number systems with a subscript of 10. And typically when we do not have a subscript, we just take that to be the decimal number system. But when we are considering other number systems, it's very important to have a designation such as the subscript 10 in this case for 382 to indicate that it is in fact base 10 or decimal. So let's take a look at 382, and we see, and you probably recall from previous studies of numbers, that the 3 represents the hundreds location, the 8 represents the tens location, and the 2 represents the ones or the unit location. So each place has an exponent of increasing value from 0. And you may not have thought about it like this, but we can start with the exponent of 0, and as we move through the higher orders or the higher place values, we increase our exponent from 0, 1, 2, 3, all the way up to n. The next number system that we consider is the binary number system. And the binary number system is base 2. So we have 2 possible symbols that we use. Again, we're using the set notation, and our various elements of this set are going to be 0 and 1. And this is going to be the lowest level of what we consider digital representation. And this could be modeled as an electronic switch that's going to either be on or off. And typically 1 will represent on, 0 will be off, but not necessarily so. We have to state that at the outset. Some of our digital electronic circuits use it just the opposite, but we won't get into that so much. But nevertheless, we have 2 different states. Again, each place has an exponent of increasing value from 0. Again, since this is base 2, we have 2 to the n descending down to 2 to the 0 power. And anything to the 0 power is going to be 1. That's critical to know when we're doing our conversion. So you see the various values descending down to 1, 2 to the 3rd power is 8, 2 to the 2nd power is 4, 2 to the 1st power is 2, and 2 to the 0 power is 1. So an example would be, how do we interpret the binary number 1001? Again, we're using 2 here as a subscript to ensure that we understand that we are dealing with binary. So when we say how do we interpret, we're really asking as humans, how do we interpret this as decimal? A computer may use 1001, but in general we would not use that for any calculation purposes. So humans work with decimal, and so we would need to perform what's called a binary to decimal base conversion. So continuing with our example of the binary number 1001, we would apply our exponents in the following way. We would note all the locations where we have a value of 1. And by location, it would be from 0 to wherever we're located in the string of numbers in sequence. So if you look at 1001, the first one in this string is going to be located at the third position. Actually, it's the fourth position with the exponent 3, because we're always starting at 0. So it would be 2 to the third power. Then we add to it the 0 from our next position, and the actual position is going to be our third position, but again, our exponent value of 2, because we're starting with 0. And in the same way, our next 0 is going to have the exponent value of 1. And then finally, we have 2 to the value of 0. So going through each of these separate calculations, 2 to the third power is 8, plus 0 to the second power is 0, plus 0 to the first power is 0, and by definition, 2 to the 0 power is 1. So adding all these up, we have the decimal value of 9, and again, we're using the subscript 10 to denote a decimal number. As a second example, consider a binary number 11111. Again, applying exponents. The first one is going to have the exponent value of 4, so it's 2 to the fourth power. And again, it's 4 because we are in the fifth position if you started from right to left, but we're starting with 0 on our exponent, so it's always going to be 1 less than the position that we're at. So 2 to the fourth power, and then moving to the next one, we have 2 to the third power, 2 to the second power, 2 to the first, and 2 to the 0 power. Performing each of these calculations separately, we have 16 plus 8 plus 4 plus 2 plus 1 gives us a final value of 31. And again, subscript 10 because we're dealing with decimal numbers in this case. So now that we know how to convert a binary string to its decimal equivalent, we might want to go the other way. We have a decimal number and we want to convert it to its binary representation or binary base. And the way that we do this is we apply successive divisions by 2, and the 2 comes in because we're going to the binary base, which is base 2, and we use the remainders of each division to build a binary sequence. And again, this is best illustrated by an example. So consider a decimal number 23. So let's start with 23 divided by 2. That equals 11 with a remainder of 1, because 23 divided by 2 will give you 11. 11 times 2 is 22, and we have that remainder of 1. Okay, so then we move on. We take the 11 that we just calculated and divide it by 2, and 11 divided by 2 is 5 with the remainder of 1. Continuing on, 5 divided by 2 is 2 with the remainder of 1. 2 divided by 2 is 1 with the remainder of 0. And 1 divided by 2 is 0 because 2 cannot go into 1 evenly. So we have 0, and then we have a remainder of 1 because we weren't really able to do anything with that division. So from here on out, we would have 0, so we don't continue on with the divisions. So the first thing that we note is we have what's called a least significant bit. And since we did our first division with 23 divided by 2, that will become our least significant bit. And then our last division will be our most significant bit, or MSB. So we put in the proper order from most significant bit going toward the right. We end up with our least significant bit. So we have the string, or the binary sequence, so to speak, of 1, 0, 1, 1, 1. And again, we use the subscript of 2 to denote that we are in fact at a binary conversion, have a binary number. So this brings us to the octal system and its associated conversions. The octal system, as the name would suggest, is a base 8 system. So the allowable symbols for the octal system will be 0, 1, 2, 3, 4, 5, 6, and 7. The great thing about the octal system is that every 3 binary digits are taken as an octal digit. And you're going to find that this makes conversion to binary much easier. And it's also one of the advantages of using the octal system is that it can limit the amount of data that we have to deal with to represent numbers, because we are using far fewer digits, as we will see in the following example. So consider a number 234, and we're going to use a subscript 8 to denote that we're dealing with the octal system. The method of conversion is to take each individual digit and convert that digit to its binary equivalent. So for instance, with 234, we have the 2 converting to 0, 1, 0, which is going to be the most significant portion, if you will, or the most significant 3 bits of the binary string. And then we move to 3, and that converts to 0, 1, 1 binary. And finally we reach the least significant digit, and that's 4, and that converts to 1, 0, 0 binary. And this is again the least significant group of 3 digits. So notice that we have 3 digits that we're converting to in binary for each 1 digit in octal. So 234 base 8 is equal to the string 1, 0, 0, 1, 1, 1, 0, 0. So we see that we have significantly less digits for the octal representation than binary. Continuing with the octal system, to convert from an octal number to a decimal number, you would multiply successfully by 8 and use exponents for the relative position of the digit. So as an example, we would have the number 234 base 8, and we would like to convert that to a decimal equivalent. We would have the first digit 2, and it would multiply times 8 to some power, and the power in this case is going to be 2, because we have the number 2 in the third position, which would have the exponent always 1 less than the position. And then we would add to that 3, which is the second digit of the octal number, times 8 again, and it's 8 because it is base 8. And the number 3 is in the second position, so the exponent is going to be 1 less than that, so it's 1. And then we add 4 times 8 to the 0 power, and again it's 0 power because 4 is in the first position, and so the exponent again is 1 less than the position number. So performing the individual operations, 2 times 8 to the second power will be 64, plus 3 times 8 to the first power is 8, plus 4 times 8 to the 0 power, again using any number to the power of 0 is always going to be 1. So this brings us to 128 plus 24 plus 4, which gives us a final value of 156 base 10. Again, we could leave the 10 off because we understand that to be, in most cases, decimal, but since we're dealing with conversion of number systems, it's always recommended to use the appropriate subscript so that we can avoid any confusion about what number system we're currently dealing with. So this brings us to the hexadecimal number system. The hexadecimal number system is a base 16 number system, and that means there are going to be 16 possible symbols that we can use in any hexadecimal number representation. So the set notation that we're showing here, we have 0 through 9 as possible digits, and so that's going to be 10 digits with that. And then we have A, B, C, D, E, and F, where A is going to represent 11, B will represent 12, C 13, D 14, E 15, and F 16. So there are 16 symbols. So the great thing about hexadecimal, much like octal, is that we can really simplify our systems because every 4 binary digits are taken as a hexadecimal digit. So again, this further simplifies any representation by using far fewer digits than binary or even octal. And this is one of the primary advantages of using a hexadecimal-based system in any underlying programming language, or either for circuit reduction and so forth, by having a base 16 system. So this starts to give you a little indication of how electronics can be simplified, and then subsequently even programming can be simplified through the different base conversions. So again, consider a very long string, binary string, that you see here: 1 0 0 1 1 1 0 0 1 1 1 1 1 1 0 1. So that's a lot of digits for any person to adequately deal with or perform any kind of calculations on, and even really a lot of digits to be represented in a electronic digital system where you would have switches representing each of these on or off states. So again, this is hexadecimal, base 16, so we can take 4 bits at a time. Okay, so picking up with the example that we started previously, we have a very long string of binary digits, and we'd like to convert that to hexadecimal. So let's take the first 4 bits of the binary string, 1001 base 2, and let's convert that to a decimal representation. And yes, I said decimal because we'll deal with that, and then we'll make the conversion to hexadecimal based on its definition. So 1001 base 2 converts to 9, and this is going to be our most significant digit. And then we have 1100 base 2. That's going to be our next 4 binary digits, and that converts to 12, a decimal 12. Well, as we introduced the hexadecimal system, we noted there was no actual 12 in hexadecimal, but there is the equivalent C. So we would have C as our next hexadecimal digit. And then we take, again, from our binary string, we have our next 4 binary digits, 1111 base 2. And that converts to a decimal 15. Again, in the hexadecimal world, we don't have a 15, but we do have F to represent that. So that's our next hexadecimal digit. And finally, we reach the last 4 digits, which is going to be 1101 base 2, and that converts to a decimal value of 13. Again, in the hexadecimal world, there is no 13, but there is the equivalent D base 16, and that's going to be our least significant digit. So each of these conversions, we'll just place those in the order from most significant to least significant, and we have 9, C, F, and D. So again, we have greatly simplified the amount of data that we're really manipulating or dealing with from this point on with this binary string, because we've converted it to base 16. And it's much more efficient from this point on to use 9CFD than all those ones and zeros that we saw previously. So if we wanted to go the other way, if we had a base 16 number, a hexadecimal number, and we wanted to do a conversion to decimal, then the way to go about it, there's several different ways. Just for simplicity, you could just go the other way. You can convert 9 to its binary, C to its binary equivalent, and create a binary string, this large string, and then convert that through the previous techniques that we've discussed to decimal. There are other techniques. We won't necessarily get into those. Also, there are calculator functions and other software that can convert these quite easily for us, but we should have a pretty firm understanding now of base conversion, going back and forth between the various bases, and really a little bit of understanding here of why we want to do that and what that gives us, the advantage that that gives us. These are just representations, and in certain cases, one representation may be more advantageous than another. Certainly if you're doing very low-level programming where you're almost at the point of considering the actual circuitry or digital circuitry with dealing with the bits, either 0 or 1, certainly you would like to stay in the binary number system. If you want to get more abstract in terms of any kind of codes for representing, you'll see a lot of applications for hexadecimal in areas of color codes and so forth, and underlying values that represent various quantities and so forth in your programming languages. So again, hexadecimal is the preferred bit system to be in at that point.